Here is the most confusing question in machine learning: how to standardize the test data. I give you three options. A. Standardize it with the mean and standard deviation of the train set. B. Standardize with the mean and standard deviation of the test set. And C. Standardize with the mean and standard deviation of the whole dataset. By the end of the video, you should be able to answer this question confidently. Hi everyone, this is Bill. Welcome to my channel. I make videos on how to do machine learning. Before I go on, if you are interested in knowing more about machine learning, please remember to subscribe to my channel. In this video, I'll explain to you what is a test set in the context of machine learning, how to standardize test data, and lastly, how to standardize for cross-validation. At the end of the video, I provide an example for standardizing test data in the context of cross-validation. When doing a regression or classification problem, it is tempting to use all the data to fit a model, and then use the R-squared value to measure how good the model fits the data. Is this a good way to measure the performance of a model? Well, the answer is no. In fact, the idea of using how good the model fits the data to measure how good is the model's prediction power is a very wrong and dangerous idea. Remember that we generate a model to predict for unseen data or generalized trend. That is very different from fitting the known data. This is very important, and I cannot emphasize that enough. So let me just say it again. The purpose of a model is to predict and generalize for unseen data, not to fit the known data. It has a huge implication on how to measure the performance of a model. We measure the performance of a model based on how much its out-of-sample predictions differ from the reality, not how well it fits the fitted data or how big the R-squared value is. Here is an example. Let's say we have px values or p independent variables and one y variable or one dependent variable. We use a linear model of the px variables to predict y. Instead of inputting all the observations into the model and use R-squared value to measure how well the model performs, we use some data to fit the model. We call this data the train set, and the estimated coefficients are the fitted model. And then input the x variables of the rest of the observations into the fitted model and predict y for those observations. Compare the predicted y values and the real y values. The smaller the difference between the predictions and reality, the better is the fitted model's out-of-sample performance. We call those data that are used to measure the out-of-sample performance test data. One thing to take note: don't ever use information from the test data to fit the model. With that said, it should be pretty easy to answer the question at the beginning of the video. How do you standardize test data? Think about it. I'll review the answer in 3 seconds. Take a pause if you need to. Both option B and C involve the test data. For option B, it is obvious. For option C, the whole dataset includes both the train set and the test set. So, some information of the test data is contained in the mean and standard deviation of the whole dataset. Therefore, the correct answer is A. Now, let's take it one step further and do a standardization for cross-validation. In my previous videos, I have taught you how to do cross-validation both in theory and in R programming. If you are not familiar with the concept of cross-validation, I highly recommend you watch those videos. I'll leave the link in the description. Basically, for cross-validation, we divide a dataset into a few folds. In this case, let's say we divide our data into m folds. Each time, we use one of the folds as the test data. In order to differentiate between a normal test data and the test data in the context of cross-validation, let's call it pseudo-test data. And the rest of the folds, which are not pseudo-test data, we call them pseudo-train set. We repeat the process m times such that each fold is treated as the pseudo-test set exactly once. If we want to do standardization for cross-validation, then obviously we should only use the pseudo-train sets mean and standard deviation to standardize the whole dataset, which include both the pseudo-train set and the pseudo-test set. Now, let's take a look at a concrete example. We have the SAT and GPA scores of 100 students. We want to use the two X variables to predict which tier of scores are the students going. The first thing we should do is to divide the 100 students into a few groups. Here, I divide them into 5 groups, each group containing 20 individuals. I use the first 80 students as my pseudo-train set. The rest of the 20 students would be the pseudo-test set. Now, take a look at the scale of SAT and GPA. The former is much larger than the latter. Therefore, we should standardize the data. Proceed by computing the mean and variance of the SAT and GPA of the 80 students in the pseudo-train set. Here you are. I have computed the mean and standard deviation. I'm going to emphasize again, these data are computed from the 80 students in the pseudo-train set. None of the information from the pseudo-test data is used in the green table. Now, we standardize the whole dataset by taking away the mean and divide the difference by the corresponding standard deviation. We then fit the standardized pseudo-train set into a model, which can be any classification method, such as logistic regression, KNN method, and decision tree. Use the fitted model and the SAT and GPA in the pseudo-test set to predict for the tiers of the schools that the 20 students in the pseudo-test set are going. Then compare the predictions and the reality. We repeat this process with different groups of students as our pseudo-test set. Each time, information including the 80 students, SAT and GPA, as well as which tier of school they are going, are used to fit the model. The rest of the 20 students' data are used as the pseudo-test set to measure the performance of the model. Each time, when you compare the prediction and the reality, you get a misclassification error. Eventually, you should get 5 of them. Add them up, and you will get the overall error, which tells you how the model performs out of sample. Not only that, you can also use the overall error to determine good tuning parameter values.